Okay, good afternoon, students.
Good afternoon, Mister.
Okay, thank you very much. Let's start our today's discussion, which is the extension of rotational dynamics. As you remember, we have said some points about moment of inertia, rotational kinetic energy, and today we are going to see about work done by rotational motion, and also about torque. But before that, what mean by rotational motion, moment of inertia? What mean by moment of inertia? What is moment of inertia? Sometimes we call it rotational momentum. Then what mean by moment of inertia? On what factor this moment of inertia depends? As you remember, moment of inertia depends on first the shape of an object, and second the size of an object, because it measures the mass distribution of an object. So it depends on the size of an object, and of course the rotational axis of an object on which the object is rotating, and third the amount of mass of an object. For example, for point mass, the moment of inertia of a body is mr square, where m is the mass of an object and r is a distance between the mass up to the rotating axis, up to the axis of rotation. And for example, for disk, it is 1/2 mr square. Then this 1/2, a coefficient 1/2 comes from the shape of an object, so it depends on the shape. And for sphere, for example, 2/5 mr square. So it depends on the shape of an object, and it depends on the size of an object, and it depends on the mass, and finally it depends on the rotational axis of an object. For example, a sphere can rotate on its axis, or it can select another axis which is out of its parts. For example, the rotational axis may pass through the edge of a sphere, or even it can be far from a sphere. So it depends on the rotational axis of an object. And a sphere with the same mass may have large size, or it may have a small size. So based on the size of an object, the moment of inertia varies. And based on this, we have some defined mathematical expression for sphere, which is 2/5 mr square, where r is the radius of the sphere. And when an object is rotating, it possesses a rotational kinetic energy. Kinetic energy, as you know, is the energy possessed by a moving object. For any object which is in motion, will possess some sort of energy called kinetic energy. Then this kinetic energy is the energy of motion. For rotating object, this kinetic energy becomes rotational kinetic energy. So rotational kinetic energy has a mathematical expression which is half of moment of inertia times omega square. A rotational kinetic energy can be obtained by a mathematical expression which is 1/2 I times omega square, where I is moment of inertia of a rotating body, and angular the omega is an angular speed or angular velocity. So rotational kinetic energy is determined by this expression, and this expression has a number of parameters or factors. For example, as you have said, I depends on 4 factors, and omega depends on the rotational speed of an object. So moment of inertia depends on the size, the mass, the shape, and the rotational axis. And in turn, even kinetic energy depends on these 4 factors. In addition to these 4 factors, it depends on the angular velocity of an object. For an object which is in rotation, its kinetic energy depends on the shape of an object. For example, for disk and a sphere, even though they are rolling on the same path, but their kinetic energy varies based on their shape and their size. And today we are going to see the third quantity, which is torque. As you know, torque is the turning effect of force. A force can bring, or a force have an rotation effect, and this rotation effects of force is called simply torque. And this torque is the tendency of a force to rotate an object about the axis of rotation. When a force is applied on a certain parts of an object, and if the object is able to rotate, then the rotation effects of force is called torque simply. So torque simply is the turning effects of force. For example, if you apply a force on one edge of an object or on the tip of, for example, our pen, then the pen may rotate. And this rotation effect, or this effect of rotation, is called torque. It is a product of force by a perpendicular distance from axis of rotation. There is an axis of there is a distance from pivot point up to line of application of force. Then a distance from line of application of a force up to the pivot point or a turning point is a perpendicular distance, and we do have non-zero force that applied on an object. There's the product of force and a perpendicular distance, or sometimes called lever arm, gives a torque. So torque is simply the product of force times a perpendicular distance. Then the linear equivalent of torque is force, as you know. For rotating objects, we call it torque, which is equivalent to force for a linear motion. And the sign of torque, as you can simply guess, it is Newton times meter, because it's the product of force and the perpendicular distance. Force is measured by Newton, and a perpendicular distance, or simply distance, is measured by meter. Then the sign of torque becomes Newton times meter. And we do have another expression for torque, which is, as you know, for force, force equals mass times acceleration. This is for linear motion, and equivalently for rotational motion. Instead of force, we can use torque, and instead of mass, we can use moment of inertia, and instead of acceleration, it is angular acceleration. They are equivalent. What a difference between these two quantities is, this one is linear, whereas this expression is for rotational motion. For rotational motion. So the difference between torque and force, they are equivalent, but force is for linear motion, and equivalent quantity for rotational motion is torque. Even though torque is the result of linear force, but we consider torque for rotating object, because the object, since the object is rotating, it produces some angle. And let's see with example. A force of 30 Newton is acting at a perpendicular distance of 3 meters from a point of rotation. Calculate the torque acting on an object. For example, if our body is this one, and if the force which is exerted on one end of an object is 30 Newton, and assume this one is a pivot point, when a force pushes the object down, then the object is supposed to rotate in a clockwise direction. And a distance from pivot point up to line of action of force is 3 meters. This one is 3 meters, a perpendicular distance from the pivot point or from the point of turning up to the line of action of force is 3 meters. Then what will be the torque? What will be the torque? Torque is force times perpendicular distance. Perpendicular distance. Then the force is 30 meters, and a perpendicular distance is 3 meters. Then what will be the torque? It is 30 times 3 meters. It becomes 90 Newton times meter. Is torque vector quantity or scalar quantity? It is vector quantity, and we use a cross product of force and perpendicular distance. Then maybe the direction will be counterclockwise or clockwise, or we can use another way to express direction. And the second problem is it's about torque. Find the torque of a body of inertia 10 kilogram meter square, rotating with an angular acceleration of 0.4 rad per second square. Here, still we are looking at torque. Then what will be torque? The given quantities are inertia of the body, which is I, and the angular acceleration of a body, which is 0.4 rad per second. Then what will be a torque? We do have two expressions for torque. The first one is torque can be obtained by the cross product of r times perpendicular distance. And the second expression is torque can be calculated by inertia times angular acceleration. These are the two expressions for torque. If force and the perpendicular distance is given, we can find torque by the product of the two quantities. In a similar way, we can find the torque if moment of inertia and angular acceleration is given. Then what will be the answer for the second expression, the second problem? Okay, for the second question, moment of inertia of a rotating object is given to be 10 kilogram times meter square, and angular acceleration is given to be 0.4 rad per second square. Then we are looking to find the torque produced by the rotating object, and the torque will be I times acceleration, and the moment of inertia is 10 kilogram meter square times 0.4 rad per second square. Then it becomes 4 Newton times meter. Here we'll not use joule because it's not an energy force. It is the turning effects of force. So it's better to use N times M instead of joule. So the sign of torque is not joule, but it is Newton times meter. Okay, the other one for a turning object or for rotating object, the body may do some work. As you know, work is the form of energy transfer. Then when an object is in some rotation or in some turning states, then it may transfer energy from one point to another point, or it can convert energy from one form to another form. Then due to this energy transfer, there will be a work done by a rotating object. This work done by a rotating object is work done by torque, because the work is done due to a turning of an object or a turning effect of an object, not by linear force, but it is by torque. Then the work done by torque is a product of torque times angular displacement. To determine or to get the value of work done during a rotation is the product of torque times angular displacement. Then this one is work done by torque equals torque times angular displacement. That is torque times angular displacement. Then to get the work done by a rotating object, what we need is the amount of torque, which is a product of force and the displacement, and the number of angle or the amount of turning angle, which is angular displacement. Then let's see with the example. Find the work done when a torque of 5 Newton meters moves through an angle of pi radian. This is angular displacement, which is pi rad, and 5 Newton meter is torque. Then the given quantities for this problem is the object is in rotation. When it rotates, the turning effects of a force is 5 Newton meter in every meter, and angular displacement is pi rad, which is a turning angle. Then what will be the work done? It is work done by torque is torque times angular displacement, which is 5 Newton times meter times pi radian. It is simply then the unit of work done, as you know, is joule, and it becomes simply 5 pi times joule, or we can use 3.14 instead of pi, or 5 times 3.14 joule, and this will be or we can leave this pi by itself is a number. We can use pi as it is, or we can use the value of pi to be 3.14. Okay, therefore, work done by a linear force and work done by the torque has a difference, and the difference is to have a linear work done. What we need to have is only a non-zero external force that is exerted on a body and a displacement. The force need to produce a displacement. Then the product of force and the displacement gives a linear work done, or work done by linear force. Whereas for work done by a torque or work done by a rotating object is the product of torque times angular displacement. The other one, even we can compare the linear quantity with angular quantities. We have linear quantities in rotational dynamics, and we do have an equivalent angular quantities. For example, for linear quantity, we can use mass simply, which is mass in kilogram. And the equivalent of angular quantity is inertia, which is moment of inertia. Moment of inertia. Moment of inertia. And the other one, the possible quantity is maybe force for linear motion, which is force. And the unit for force is Newton, as you know. And the equivalent for angular quantity is torque. And has different units. For force is simply Newton. And the other one is maybe there may be a linear kinetic energy, which is 1/2 mv square. And for rotational, it is rotational kinetic energy, that is 1/2 I times omega square. And for force, as you know, the expression for force is mass times tangential acceleration or linear acceleration. And for torque, the mass equivalent in rotation is inertia, and the acceleration equivalent in rotation is angular acceleration. So these are the possible expressions in rotational motion. And work done, as you know, work done by a linear force is force times distance. If a certain force is exerted on an object and the object is able to displace a certain distance s, then the product of force and the displacement gives work done by a linear force. And similarly, work done by torque is torque times. It is torque times. Instead of s, we can use theta. Therefore, torque or turning effect times theta gives an a work done by a torque. Then these are the possible angular quantities, the right quantities which is listed at the right side as the possible angular quantities, but not only this one. There are a number of equivalent quantities, but these are the basic one. For example, for mass, we have moment of inertia, and for force, we have torque with the same concept. And for kinetic energy, we do have rotational kinetic energy. And for force, we do have a torque. And for linear work done, there is a rotational work done. So you need to summarize these points. For every quantity in linear equation, there will be an equivalent angular quantities. For mass, there is moment of inertia, and for force, there is torque. But they have nearly the same concepts with some difference. For kinetic energy, there is rotational kinetic energy, and for force, the product of mass and acceleration gives a linear force. And instead of mass and acceleration, we have to use moment of inertia and angular acceleration. And for work done, is a product of, as you know, is force times distance, and for torque, it is a product of the product of torque times angular displacement, and the unit for work done is, as you know, as a joule. But this theta need to express in rad, not in degree, not in revolution, but it should be expressed in rad. And finally, we can ignore the units, and we can express only by using joule. And we have a simple activity as a physical problem that tests your understanding for work done by a rotational motion. And the problem says how much work is needed. Needed to be done on a disk of rotational inertia 0.03 kilogram meter square to accelerate it from rest to an angular acceleration of 200 rad per second square in 2 seconds. The problem takes, or the motion takes 2 seconds, assume, and some quantities are given. Some quantities are provided to you. The first one is moment of inertia, which is 0.03 kilogram meter square, which is moment of inertia. And the other quantity that given is initial angular velocity, which is 0 because the motion starts from rest. It is started from rest. And the other one is angular acceleration, which is 200 rad per second square. And the rotation attains this acceleration for 2 seconds. So time is given, which is 2 seconds. Then the required quantity is a work done. So what will be a work done by? A torque, not by linear force, but work done by a rotating object, or work done by a torque. How can we get it? This problem has an intermediate result. First, we have to have its theta. As you know, work done by torque is torque times theta. But here we don't have theta and tau, or we don't have theta and torque. So we have to have first theta and tau from this expression. Then how can we get tau and how can we get theta? Just to get this, what we need to do is we have to have the product of moment of inertia of a body times angular acceleration. Two of them are given. The inertia is 0.03 and acceleration is 200, and it becomes 6 Newton times meter. And the second one is quite tricky because you have to recall the expression of motion, which is from distance for linear distance equals initial velocity times time plus half of a times t square. This one is for linear. And for rotational, we have to use the same expression. Instead of initial velocity, initial angular velocity times time plus 1/2, but instead of linear acceleration, we have to use angular acceleration times time square. But fortunately, this becomes 0 because the motion starts from rest, and the rest one will be 1/2. Acceleration is 200, and the time is 2 seconds square. Then this becomes 400 rad. This is 400 rad. And we do have two quantities, which is torque and angular displacement. Then we are in the right track to get the work done. And the work done by torque becomes torque times angular displacement. And torque is 6 Newton meter times 400 rad, and it becomes 2400 joule, because this rad has been ignored here. No need of using rad, because we know the unit of work done is joule, so we don't need to use the unit rad. We have ignored the unit rad and have expressed energy by joule only. Is clear? Okay. Do you have any question? If you don't have question, let's summarize it. Today we have discussed on 2 points. The first one is torque, and the second one is work done by torque. When you say torque, it is one of the quantity in physics, which is a turning effect of force. Force sometimes bring a translational motion, or it can bring a rotational motion. If the result of force is rotating, then it's said to be a torque. And a torque is a tendency of a force to rotate an object about axis of rotation. So an object, if an object is rotating, there should be an axis of rotation, unless it becomes translational motion. Then the product of force and the perpendicular distance from axis of rotation is called torque. So torque is simply force times perpendicular distance. The linear equivalent of torque is force, as you know. For linear, it's force, but for rotational, it becomes torque. And the SI unit of torque is not joule. Bear in mind this, it is not a joule, even though they are equivalent, but it's not formal to use joule. But the formal one is Newton times meter. And the other one is about work done by a torque. If an object is in rotation, then there will be energy transfer. And this energy transfer, the process of energy transfer is called work done. And then this work done numerically can be obtained by the product of torque and angular displacement. Then the torque, the product of torque times angular displacement, is a work done by torque. And the unit of work by a linear force and the unit of work by a torque, for both it's joule. And the other one is the linear equivalent of the rotational equivalent of mass is moment of inertia, and the rotational equivalent of force is torque, and the rotational equivalent of linear kinetic energy is rotational kinetic energy. For linear, if you use 1/2 mv square, then the rotational becomes 1/2 I times omega square. And for force, if you use for linear mass times acceleration, then the torque becomes inertia times angular acceleration. And similarly for linear work done, F times S, but for rotational, it becomes torque times theta. And then you can get questions or problems in your textbook, then you need to practice it. Okay, thank you very much. Do you have any question? If you have any question, please, you will come. Anyone? What's the question? So if you don't have question, thank you very much.